Welcome everybody to this first seminar in December of the European Astrobiology Institute. And the speaker today is Catalina Plesa. She is from the German Aerospace Center from the Institute of Planetary Research. And she's also leading our working group on planetary environment and habitability. So if you want to take part in this working group, please just contact her. But now I will open the floor for our today's speaker, and there will be then ample possibilities for asking questions and doing discussion contributions. So welcome, Catalina, and the floor is yours.
Thank you very much, both, and I'm very happy to see so many of you online today. So my name is Anna Plesa. I'm working at the German Aerospace Center. I'm leading a junior research group there. And today I will be talking about the exploration, the subsurface of exploration of the environments of Mars and Europa. Now, when we look at habitable environments, when we look at the requirements for habitability, we see that we need water and we need an energy source in order to drive cell metabolism. Also, we need chemical compounds as nutrients to be available over sufficient time in order to drive life, basically. And when we define the habitable zone, this is the region around a star where an Earth-like planet can have liquid water on its surface. And you see here this diagram showing the habitable zone, and you see here the mass of the star relative to the sun and the radius of the orbit relative to Earth's orbit. And you see that in the solar system, the Earth lies within this habitable zone. We know that on the Earth we have water at the surface, and Mars and Venus lie at the edges of this habitable zone. Now, in terms of surface and subsurface habitats, we know that on the Earth we have both surface and subsurface habitats. We know that on Mars we once had liquid water at the surface, and we have perhaps today liquid water in the subsurface. But also we have these bodies here in the outer solar system, the icy moons of Jupiter and Saturn, like for example here Europa and Enceladus, where subsurface habitats may exist. Now, when we look at the classification of habitable environments, we can follow the classification by Lammer et al. In 2009, and we see here a class 1 habitat are those habitats suitable for the evolution of multicellular life forms on the surface. And this is classical habitable zone definition. So basically, Earth would be a typical example for this kind of class 1 habitats. Class 2 habitats are those where microbial life may have evolved and habitats in the subsurface have remained. And this typically refers to inner and outer edges of the habitable zone. And Mars, for example, is a classical example for this kind of habitats. Now, we also have class 3 habitats where life forms may have evolved and populate subsurface water oceans. And this is typically for bodies beyond the ice line. And in this class, we have, for example, Europa and Enceladus. And here in this presentation, I will focus on Mars and Europa, and I will show you how what can we do in terms of modeling in order to place constraints and to investigate the subsurface environments of Mars and Europa, where potential liquid water may exist today. And we will start first with Mars. Now, as I said before, we know that on Mars we have once had liquid water, and we see the traces of this past liquid water on the surface of the planet in terms of valley networks, outflow channels, deltas, hydrated minerals, and also these features here called recurring slope lineae that might indicate that potentially today water may still be existing in the subsurface. Now, today, liquid water is no longer stable at the surface of the planet, and this is due to the temperature and pressure conditions that we have on Mars. However, liquid groundwater may still exist in the subsurface, And this is what we will look at in the next couple of slides in order to understand how we can constrain the presence of liquid water in the Martian subsurface. But when we talk about liquid water, we have to acknowledge the information that we have in terms like, for example, the radar observations from the Mars radar on Mars Express, which suggests the presence of a liquid reservoir underneath the south pole of Mars. And here you see a radagram where you see these bright radar echoes that suggest the presence of liquid water. And this has been determined, the strong radar signal has been determined at about 1.5 kilometers depth and in an area of about 20 kilometers large. And this is, of course, a bit surprising because the temperature at this location is very small. It's very cold, and therefore it would be difficult to have liquid water below at those latitudes. However, this may not be pure water, but water containing a significant amount of salts that will depress the melting temperature and therefore could sustain liquid briny solution there. Now, here you also see a map where you have different rovers and landers on Mars, and you see here the Phoenix lander, which landed close to the Martian pole, North Pole, and here you see an artist's conception of this lander with the solar panels and the instruments on the deck. And what was also surprising here was to see these droplets on the lander leg, which were indicative of, or they're similar to droplets of water. And basically, laboratory experiments suggest that this kind of droplets contain chlorides. These are again salts that depress the melting temperature of water and of water ice, and therefore can sustain liquids, water in liquid form to smaller temperatures, to lower temperatures. And we also have indication of subsurface ice. As you can see here on this map at the top, you see a map of subsurface water ice depth, the water ice depth. Here in magenta colors, you see regions where water ice is much closer to the surface. And basically, this has been determined by looking at the thermal inertia measurements. And basically what you can think of when you have ice, then you could have at the base of the cryosphere, at the base of this ice layer, you could have liquid water. This may not be pure water, but a salty solution, a saline groundwater. And the distribution of the ice and also of the liquid water depends on the local conditions. And what we can do, we can look at numerical models that we can then combine with the observations at the surface, like geomorphological features or maps of subsurface water ice, in order to identify regions and depths at which liquid water may still be stable today. But in order to do so, let's take a look at critical parameters that influence the potential groundwater table depth. Here, for example, we can categorize this into near surface parameters. These are, for example, the melting temperature, which depends on the amount and distribution of salts. And you see here on the right-hand side a plot showing the melting temperature of water ice as a function of pressure. And what you see here is how this temperature changes when we include salts, in this case perchlorates like sodium, magnesium, and calcium perchlorates in eutectic concentrations. Now, in addition to the melting temperature, the crustal thickness distribution and the thermal conductivity of the crust play a major role in the distribution of the groundwater table depth. This is due to the fact that the crust acts as an insulating, as a blanketing layer, and keeps the subsurface temperatures warm. Also, the surface temperatures that depend on the obliquity variations can affect the groundwater table depth. And there are also more deep interior related parameters, like, for example, heat sources, their amount and distribution between the mantle and the crust can locally affect the depth at which groundwater may be stable today. and the convection pattern, the size and distribution of mantle plumes, as you can see here. So these are hot thermal upwellings that transport heat from the deep interior towards the surface, and they may introduce variations locally in the groundwater table depth. But how do we do this in our models? So how can we use this kind of models in order to place constraints or to make predictions of the cryosphere depth or the groundwater table depth? Well, what we do, we use this global thermal evolution models, as you can see here, and we combine them with the crustal thickness distribution, as you can see on this map here. And this crustal thickness distribution is derived from gravity and topography data. Now we let the models run for the entire thermal evolution of the planet, and then we calculate the distribution, the present-day temperature distribution, and then we compare this temperature at each location basically with the melting temperature. And then we can say at each location how deep the groundwater table depth could be. Now, what you can see here, the effects of the crustal thickness is mainly evident in basins, like, for example, here, Hellas. You see this, Utopia. You see that there, the groundwater depth is located deeper below the surface. And you see that in regions, for example, like Tarsis or even Elysium here, the groundwater table depth is closer to the surface, and this is due to the fact that the crust is thicker there, provides a more stronger insulating effect, and therefore keeps the temperatures warmer in the subsurface. Now, what is important to mention here also is that we use variations of the surface temperature, and they give general water table depth trend with latitude. As you can see here on this plot, we have a deeper cryosphere at the north and south pole compared to the equator. And this is due to the fact that the surface temperature is colder at the north and the south poles of Mars compared to the equator. And we can take a look in more detail at each of these parameters. And by doing so, we can place constraints on the cryosphere depth distribution today, but also during the thermal evolution. So we can take a look at how this depth has evolved during the entire thermal history of the planet. And then we can combine this kind of models with diverse data sets from geomorphology, spectroscopy, and mineralogy of the Martian surface in order to identify regions where liquid water may be located close to the surface and regions that are potentially interesting for future exploration. So to take a look at the effects of each and every parameters, for example, we can take a look at the effects of the surface temperature. Here you see two models. In one of them, we have varied the surface temperature with colder temperatures at the pole compared to the equator. And here on the right-hand side, we have another model where we have a constant surface temperature. And you see basically what I have said before, that the surface temperature variations give the distribution of the water, of the groundwater depth with latitude. In this case, where we have a constant surface temperature, you see that basically the groundwater depth distribution follows the crustal thickness distribution. Now we can also look at the effects of the crustal thickness variations, and here we have two models. In one of them, we have the variable crustal thickness, and in the other one we have a constant crustal thickness. You see here again the cryosphere depth at present day, and you see that here the crust varies between 15 and 150 kilometers, and you see the variations due to the crustal thickness are both with latitude and longitude. Whereas in this case, you see that if we don't have crustal thickness variations, then of course the groundwater table depth follows the surface temperature pattern, with colder regions at the poles compared to the equator, and therefore a deeper cryosphere at the poles compared to the equator. Now, in terms of crustal thermal conductivity, this controls the temperature distribution in the subsurface layers, and basically it does so through the blanketing effect of the crust. So here we have two simulations in which we have a thermal conductivity of the crust on average of 3 watts per meter Kelvin, whereas here we have a lower conductivity. And the low conductivity means that we promote a better insulating effect of the crust, and therefore the subsurface temperature is higher. So basically what you see here is that the groundwater table depth here shifts closer to the surface compared to this other model, and it does so by about 2.5 kilometers on average. Now we can also take a look at the effects of mantle plumes. These are these thermal upwellings that transport heat from the deep interior towards the surface. And what you see is that their effect is relatively minor. And this is because the cryosphere depth variations are more sensitive to the variations in temperature close to the surface, and less sensitive to the variations in temperatures deeper in the interior. So here we have two models. One has a more pronounced effect of the mantle plumes, whereas the other one has a less pronounced effect of the mantle plumes. And you see that they're pretty similar. The cryosphere depth distribution is pretty similar. We see some subtle differences, maybe in basins, like for example here in Hellas. You see that this is slightly deeper compared to this model, and maybe around the equator, but the variations are very small. Now, we can also take a look at the effect of heat source distribution. So heat sources are incompatible, and they are typically enriched in the crust when the crust is being formed. And therefore, the crust is typically more enriched compared to the mantle. Now here we have two models in which we have, in one of the models, we have a limited amount of heat sources located in the crust, only 20% of the total bulk amount of heat producing elements. And in this other model here, we have nearly the complete amount of heat producing elements being located in the crust. And what you see here is that they accentuate the variations in the cryosphere depth, which are given by the crustal thickness. And this is due to the fact that in the regions where we have a thick crust, it's not only, we don't have only a better insulating effect due to the crustal thermoconductivity, but also we have higher temperatures due to a higher amount of heat sources that are available here, compared to, for example, basins where we have a less insulating effect. The crust is thinner here, and therefore we have a less insulating effect of the crust, but also a smaller amount of heat sources that can increase the temperature, and therefore the temperatures are lower in these regions. And we can also take a look at the effects of salts. And here you see, again, the melting temperature of pure water ice, here in this diagram at the right-hand side. And here you see a model corresponding to a model where we have computed the cryosphere depth according to this melting temperature. Now we can include salts in eutectic concentration, like for example sodium perchlorate, and here calcium perchlorate. And basically what we see is that the groundwater table shifts closer to the surface, and it does so by about 4 kilometers on average here, and by about 7.5 kilometers on average here. And you see that the closer it goes, the higher it goes towards the surface. The groundwater table depth variations mainly depend on the surface temperature variations, and less so on the crustal thickness variations. You see some subtle effects. For example, here, if you look at the poles, in the North Pole, we have a slightly deeper cryosphere compared to the South Pole. And this is due to the fact that the crustal thickness at the North Pole is thinner and has a less insulating effect compared to the South Pole, and therefore the temperatures in the subsurface here are colder compared to the South Pole. So to conclude this part, we have seen thermal evolution models that can help us predict the cryosphere depth distribution. And in order to understand the subsurface conditions on Mars, we need to study the entire thermal evolution. Now we have seen in the models that if we include surface temperature variations and crustal thickness variations, that the water table depth lies at about 2 to 5 kilometers in the Tarsis region, and at about 20 kilometers close to the North Pole. And this is the combined effect of the crustal thickness variations and of the surface temperature variations. Now, we also observed in the models that for the northern polar region, we have a water table depth that is located about 1.5 times deeper compared to the South Pole, and this is due to the fact that the crust at the North Pole was in this calculations thinner compared to the South Pole, and therefore has a smaller insulating effect. Now, if salts are present in eutectic concentration, they can significantly reduce the depth to the groundwater on Mars, and this can be done by about 7.5 kilometers on average and up to 13 kilometers locally. Now, at the moment, it's very difficult to constrain the groundwater table depth on Mars, and this is due to the fact that radar sounders like Chloride and Marsis are very sensitive to attenuation, and they have difficulties in sampling depths below hundreds of meters, especially if we search for aquifers that are smaller than tens of kilometers and further away from the polar caps. But there are payload concepts like, for example, volatiles and live key reconnaissance and in-situ exploration that proposes to use a transient electromagnetic sounder that would be capable to detect the presence of salty water at depths of kilometers. It also proposes to use a drill that would be capable to access depths of tens of meters or even more. And if you want to know more about this kind of technologies and also about future steps for Mars subsurface exploration, I refer you to these white papers listed here. Now let's take a look at the second environment here in this presentation, namely Europa. And on Europa, we know that we have presence. We have very well indications that we have the presence of an ocean, of a salt ocean underneath. Basically, what we see at the surface Europa, we see a variety of geological features, like for example, here you see the chaos terrain, you see domes, you see lenticulae that hint at processes that might be active in the ice shell, and both the ocean and to some extent the ice shell may contain impurities like salts, for example, that may affect the dynamics in the ice shell, the large-scale dynamics in the ice shell, and in turn affect what we observe at the surface and can explain what we see at the surface. Exact processes that take place within the ice shell and in the ocean are poorly constrained. It can be that we have, for example, here a water ice interface with a mushy boundary layer, like indicated here, where salts are being transported into the ocean. Now, if salts are present in the ice shell, large-scale dynamics in the ice shell could redistribute the salts, and we might also have, for example, here liquid reservoirs in the ice shell due to large-scale upwellings, as you can see here on the sketch. So in order to understand basically what we observe at the surface, we need to understand processes that take place into the ice shell. And this is what we will look at in the following slides. Now, one indication that we have and one surface structure that is mostly related to the presence of liquid reservoirs below the surface is the so-called chaos terrain. And you see it here. This is a chaotic topographic feature at the surface of Europa, and it could indicate the presence of a liquid pocket, for example, liquid reservoirs in the ice shell. And this has been suggested, this kind of mechanism that I'm presenting here has been suggested to be responsible for the formation of this chaos terrain. So basically we have a rising thermal plume, as you can see here, and you see here an upwarding surface due to the plume that impinges on the lithosphere. You have here an eutectic surface, and you have here potentially salts that are contained in the ice shell. Here, when this region here melts and forms a lens, you have a deflection of the surface due to volume change, and you create these kind of fractures and hydraulic flow that then creates this kind of blocks, floating blocks into a briny layer, and the lens here collapses. And when it refreezes, it can form this kind of feature that we observe at the surface, this so-called chaos terrain. Now, one thing that is important to note here is that when you look at the temperature distribution in the ice shell, so here's a sketch, here being the surface, here being the ice-ocean interface, you see here typical temperature profiles. For example, here a conductive temperature profile where the heat is being diffused through the ice shell, and you see two other temperature profiles more representative of a large-scale dynamics going on in the ice shell. And here, for reference, you see the solidus of pure water ice. Now, in this case, what you can see is that it's difficult to melt if you have pure water ice. But if you include salts, then you can locally decrease the solidus and obtain melting of the ice shell, as has been suggested here, to obtain this kind of liquid reservoirs in the ice shell. And we have indications of salts at the surface of Europa, like, for example, the spectral signature that has been observed by the Galileo near-infrared mapping spectrometer. And this salts, the signature you see here on this plot, here the colors indicate non-icy material in red, and in blue more icy material. And you see here the observed spectra in these two colors, in red and blue. And as a comparison, you see spectra from sulfates and from clays. You see that clays cannot explain the spectra that has been measured, but for example, sulfates like epsomite here could explain, can very well explain the observed spectra. Now, a more recent study has found indications that irradiated sodium chloride is a best match for higher resolution data from Keck Observatory. And you see here the measured, the observations and the measured spectra in the laboratory. And what's interesting here, so sodium chloride is basically table salt. And what's interesting here is that this data, this spectral data, is has been observed in a region, in a young region that is also associated with this chaos terrain, and it might be indicative of an endogenous origin of this salt that we observe at the surface. So basically, in order to understand the surface observations and the surface features at the surface of Europa, we would need to understand what happens in the ice shell. And for this, what we have done, we have looked at how, for example, salts can be transported through the ice shell. Here, for example, we have 3 different scenarios with an initial distribution of salts in the ice shell. You have here the density that indicates the amount of salts. So the closer you go to the surface, the more salts are incorporated there. And the deeper you go in the ice shell, the less salt can be incorporated. So in this one scenario here, we have a linear scenario in which we assume that we have a fast freezing scenario and that salts can be incorporated throughout the ice shell. In these other 2 scenarios here, we assume that we have an initial fast freezing where salt can be incorporated efficiently in the ice shell, but then with time, salts are less and less incorporated in the ice shell. And in this case, we have a briny layer that is present at the ice-ocean interface. Now, here, what I need to mention is that salts are, of course, incompatible, and usually they go into the ocean, and they can be trapped in the ice shell only if the freezing rate is very, very fast. And this might be, of course, the case in the early stages of freezing of the ice shell. And what we do here, we investigate the mixing and the spatial distribution of salts, and we do so by using geodynamical models. So we use at a large scale dynamics of the ice shell. Here you see again the distribution with the initial exponential and layered profiles. These two profiles that have a high concentration of salts towards the surface, but then less so with depth. And here you see the initial layered profile where we have the incorporation of salts throughout the ice shell. And then we take a look at what happens when we start our simulations and look at the global dynamics in the ice shell. So what you see is that we have an overturn of this initial unstable density profile, and we transport high salt concentrations towards the ice-ocean interface. However, the highest salt concentration remain trapped close to the surface in a so-called stagnant lid. This is an immobile layer that forms at the top due to high viscosity that is caused by the small surface temperatures. And we can take a look what happens with time, and we see basically that in case of the initial linear profile, at the end we have a stable configuration, and we have a stable configuration that also does not allow for large-scale mixing in the ice shell. In the other two scenarios, we have transported salts towards the ice-ocean interface, but some small amount of salts are still being redistributed in the ice shell. And in all of the scenarios that you see here, this layer remains trapped close to the surface. And in this layer, as you can see here, we have a high salt concentration. Now we can also take a look at the amount of salts that we assume for the ice shell. So what we have done here, we have performed additional calculations in which we have varied the amount of salts in terms, and you see this here in terms of the density contrast between the salty component and the pure water ice component. And we have varied this density contrast corresponding to about 0.6 to 5% compositional density variations due to salinity. We assume here for simplicity just one of the previous profiles of salt distribution, and you see here this is the initial fast freezing scenario, and there are more moderate or slow freezing rates, and then we have here a briny layer at the ice-ocean interface. And here you see these three scenarios with a different density contrast representing basically different salt concentrations. And you see again a similar scenario as before. So most or the highest concentration remain trapped in the stagnant lid. But what you can observe here is that in small quantities and so in small concentrations, salts can be redistributed through the ice shell. And you see here even in this case, an even almost homogeneous mixing. So to conclude also this part, in terms of the distribution of salts through the ice shell, if we have an initial layer distribution with a relatively high concentration of salts, then the ice shell becomes conductive with a stable salinity stratification. But in all other scenarios, we observe that some mixing takes place in the ice shell, with some of the salts being transported through the ice shell. And most of the salty components remain trapped here close to the surface in a stagnant lid. And if you remember the scenario that has been proposed to explain the chaos terrain, this is compatible by having salts close to the surface, and we could have plume-induced melting of this heterogeneous layer and then create this kind of surface feature that we observe on Europa. In terms of the future subsurface exploration of Europa, there are two missions that will visit Europa in the near future. So the JUICE mission, this is an ESA mission to the Jupiter system that will characterize Jupiter, Ganymede, Europa, and Callisto, and will have two flybys at Europa at an altitude of about 400 kilometers. The planned launch for this mission is in 2022 and will arrive in the Jupiter system at 2029. The Europa Clipper mission is a NASA mission which is dedicated to Europa and dedicated to characterize this Jupiter's moon habitability. It will have 45 flybys at Europa at altitudes between 2,700 and 25 kilometers, with most of the flybys at altitudes below 100 kilometers. And the planned launch for this mission is by 2025. And both of these missions will improve our understanding of the both of the composition of the known icy material on the surface, but also on the presence of subsurface water water reservoirs, liquid reservoirs. And also will help us understand the habitability of Europa's ocean through composition and chemistry, and the formation of surface features and active processes on Europa. So to conclude, in this presentation, I have discussed how to use numerical models and what we can do in terms of numerical models in order to investigate the subsurface environments of Mars and Europa. On Mars, we see that the water table depth lies at about 2 kilometers in Tarsis and about 20 kilometers close to the North Pole. And we see that salts, if they are present in large concentration, they can reduce the depth of to the groundwater by about 7.5 kilometers on average and up to 13 kilometers locally. Now, for Europa, salts also play a major role, and we see that if they are present in the ice shell, some degrees of mixing can take place, and they can be redistributed through the ice shell. And we see that most of the salts remain trapped in a stagnant lid, in an immobile layer close to the surface, that can be then have plume-induced melting of this salty region in order to form the chaos terrain, as has been suggested in previous works. So with this, I will end here. Thank you for your attention, and I'll be happy to answer questions.
Many thanks to Ina. And now when you want to ask a question, please switch on the video and wave to us, or just switch on the camera so that we can see you. Unfortunately, there is no function where we can actually raise your hand in this kind of program as opposed to Zoom. So if you want to ask a question, just switch on the camera, and then, or you can also enter it into the chat if you don't really have a camera at your disposal. So please go ahead.
Hello.
Hi.
Yes, Michelle, please.
Hi. Well, just to break the ice, because my colleagues seem to be. Okay, just one question, because you mentioned these white papers. In fact, I was evaluating some of them. And don't you think it is, in particular, is too optimistic saying that some of these instruments can be going deeper, the drillers, I mean, than 10 meters, because this is quite challenging. In fact, it will depend on the type of terrain. Thanks.
Okay, thanks. So in fact, one of the suggested investigations or instruments was this transient electromagnetic sounder, and this could reach indeed depths of kilometers. Go to the slide. Oops. Here we go. Okay, and this could reach indeed depths of kilometers, because it measures basically the magnetic induction of this salty reservoir at depth.
Yeah, sure, but I was meaning the driller. Okay, the drilling machines.
The drill.
Yes.
Yes. So these are all being tested at the moment, and I think that there are very promising tests and very promising results. There have been testing campaigns, and of course it will depend on the material that we encounter. But this will basically, this drill will kind of drill in the subsurface and I think we're quite confident that we can reach depths of tens of meters or even larger.
Okay, thank you.
Hi, Ina. If
Okay,
I may, I can't switch
Joseph,
on my
please.
camera, but I can switch on my microphone. So maybe I can ask you questions without, opening the camera. One of the explanations for the European ocean to exist to begin with is tidal heating in the ice shell. Now, I know this is in competition with tidal heating in the silicate layer, but I think at the moment we cannot really decide between the two, if I'm not mistaken. Now, did you take tidal heating into account? It seemed to me you did not. And how would that change, your conclusions? Also, for tidal heating, the thickness of the ice shell would be important. And I didn't really get, what the thickness of the ice shell that you assumed actually was.
Yes, so indeed, in these simulations were very, very simple in terms that we did not consider tidal heating. And I'll have to switch to the simulations again. So basically, if we have tidal heating, then you would affect also the temperature distribution in the interior, and tidal heating will probably be more pronounced where you have thermal upwellings in the ice shell, and therefore would be even more able to promote melting. In addition to the fact that when you have salt, you decrease the melting temperature. If you have tidal heating, you also increase the temperature of the upwellings, and therefore would be more easy to produce melt in the ice shell. In terms of the ice shell thickness, here I used a very generous ice shell thickness of about 70 kilometers. Now I think most of the studies assume a thinner ice shell, and this is what we are doing right now. So we are looking at this kind of simulations for a variety of ice shell thicknesses. And this can affect, of course, also the transport of chemical heterogeneities in the ice shell, because it affects the vigor of convection or the vigor of large scale redistribution of heterogeneities. So this is what we are working on right now.
Okay, then there was a question by Josep. Gregor? No? Then I would like to go to the chat question. There was a question by René, and it says, do you think you can expand your models to trans-Neptunian objects like Triton, Haumea, or Varuna?
Okay, let me, I'm also, oh, okay. Yes, so in principle, we could apply this kind of modeling to various rocky planets or icy satellites. Right. What we are doing here, we're looking mostly at the large scale redistribution of material in the ice shells and in the silicates. And this can be applied to different objects in the solar system and beyond.
Okay, the next question was by Jan Kostlats. How do you think? Is there any evidence of current lava-water ice interaction on Mars?
I'm not sure if I'm the right person to ask about this. So in principle, we have observations that water ice is present in the subsurface, and of course we have the poles on the polar caps on Mars. But we don't have, at least we have not detected active volcanism on Mars. There are areas that are very that have been suggested to have had recent volcanic activities in Tharsis and in Elysium. These are the large volcanic centers on Mars, but there also the question is how much ice is present in the subsurface at those locations. So the maps that I've showed you shows the distribution of potential liquid water in the subsurface of Mars, and this assumes that if ice is present, then you'll have liquid water at that and that depth in the subsurface. But this also requires that you have ice at a specific location on Mars. So, and this is something that we can constrain then with observations and looking at geomorphological features and at the distribution of water ice that I've showed in terms of maps.
Okay, there is another question by Raoul J. My question is, when Europe has a subsurface ocean, why shouldn't we focus on icy moons rather than Mars? Is it possible to confirm the subsurface ocean in Europe in future missions?
So I think Tilman also mentioned this. So we have very strong indications that we have a subsurface ocean on Europa, and this we have both from observations from orbiters that have measured the magnetic field induction signature, and also, for example, from ground-based observations where we see signatures of water vapor plumes. Now, one thing that is different between Mars and Europa is that Mars is much easier to reach. So to send a mission to Mars is easier compared to Europa. And on Mars, we have indications that we have liquid water on the surface, and most likely some of this water is now present in the subsurface. So I think it's basically both exploration of Mars and Europa will help us understand about subsurface habitable environments.
Okay, the next question is by Gabriel Gonsalves, and he wonders, a lot is said about the presence of perchlorates in the Martian brine. Do you think that due to high concentration of carbon dioxide in the atmosphere, carbonates could also be present in high concentration in those subsurface waters?
I'm not sure that carbonates have been detected in high concentrations on Mars, so I'm not aware of that. Might be that there are other studies, but I don't know that carbonates have been found in large concentration in large quantities on Mars. So I cannot really comment on that.
Yeah, because on our Earth, the carbonates are mostly sedimentary, and this is not really working on Mars, and Mars is mostly volcanic. So it's not really so evident that you have lots and lots of carbonates in the water. Then there is a question by Felipe Gomez. I was wondering if it could be possible to model the time of water stabilization versus depth, I think it was meaning.
So in principle, in our models, we can look at different times in the evolution and look at what depth water may have been stable in the subsurface. This is something that we already do in our models, and this is something that can be used in order to also compare with specific surface features at specific times during the evolution of Mars. So this is something that we're working on right now.
Then, by Ludwig, there is another question. Are there any new discoveries, data advancements you could see being made before the arrival of new satellites in Europa?
Well, I think the one study that I've mentioned that has found the presence, or at least has found that irradiated sodium chloride can explain very well high-resolution spectral data that has been obtained with Earth-based observatories. That is something very interesting, and it kind of gives us an idea about the composition that one could expect. I mean, it doesn't necessarily mean that this sodium chloride is present in the subsurface ocean, but it is a good indication for it. And this kind of observations we can use in order to feed our models with them, and then try to understand how this affects our results.
Another question is by Raoul. What kind of biosignatures could we expect from Europa?
Yeah, well, in principle, yeah, I'm not sure I can answer this question. This is probably something for our biologists in our working group in the European Astrobiology Institute, and I'm sure that they could explain in much more detail what kind of biosignature we could expect and we could measure on Europa. So if there is anyone online that can comment on this, please feel free to do so.
Well, here's Jean-Pierre. I just would like to thank you for this very nice talk. And just to give a just short answer, well, it's more speculative, but we have just the reference system on Earth, and this means that we are sticking then on the specific organisms in oceans, or some bio-related pigmented or whatever membrane components which are living in oceans and close to cryospheric areas, so just to the polar regions. Such kind of organisms can be a reference, and then studying these organisms and particularly the chemistry should be a good hint for biosignatures on Europa or even on Enceladus.
Thank you, Jean-Pierre.
Okay, then there is a question by Tilman Spohn. You gave an estimate of the depth to the water table. This is, of course, largely uncertain. Can you instead give a reasonable range of values?
Yeah, so in principle, what we see in our models is that the depth of groundwater on Mars can be up to, I mean, this is highly variable, of course, depending on the location. You have a shallower depth at equatorial regions compared to the poles, and this is due to the fact that the surface temperatures are higher at equator compared to the poles. And in addition to that, it very much depends on the crustal thickness variations, of course, and maybe the most important thing is the distribution of salts, because they can significantly decrease the melting temperature. Now, taking all this into account, we can say that, for example, for the equatorial region, we expect, especially in regions that are covered by a thick crust, depths of up to 2 to 5 kilometers, so the liquid water depth of 2 to 5 kilometers, but much deeper at the poles, like, for example, more than 18 kilometers, 18 to 20 kilometers. But as I said, it's very difficult to constrain without comparing with specific observations, and this is the idea, basically, to combine these kind of models with observations that we have in order to place more robust constraints on the depth of liquid water. Because at the moment in our models we make assumptions, and we can test these assumptions by comparing our results with what we observe in terms of geomorphological structures at the surface when they were formed, and also, for example, if we have maps of the distribution of subsurface water ice, then we know that at that location we have water ice present in the subsurface, and then we can take a look at our models, what kind of depths we would get in terms of liquid water at those locations.
Amy Wiggins wants to ask a question. Biosignatures that we can detect on Earth, or it's maybe a comment, is biosignatures we can detect from Earth will be organic molecules in plumes, but it's hard to determine whether they have a biological origin. Identifying an atmospheric disequilibrium would be awesome, but sadly Europa has, as it's known, a significant atmosphere. I think that was more a comment. Any further questions or comments? If not, I think we have spent our hour quite nicely. Many thanks for all for attending. Our seminar will be available on YouTube as very soon, and we're looking forward to seeing you again at the next seminar.
Thank you, everyone. Thank you, both.
Thank you and goodbye.
Thank you very much anyway.